Hi everyone, it's me again, Felix from Lightware UK. I've also got Phil here.
Hi.
Phil's going to be answering your questions, so if you guys have any questions, feel free to put them into the chat. And today we're going to be talking about HDBase-T, the basics of fiber optic transmission, and at the end we do a little bit on DisplayPort. Cool. So let's get into it. So before we get started with HDBase-T, it's worth just taking a little bit of a look at the structure of a DVI and HDMI cable. So the most important wires in this cable are the TMDS wire pairs. So in the DVI or HDMI cable, there are 4 TMDS wire pairs. 3 carry the color information and 1 carries the clock channel. And you can see that these are high-speed unidirectional channels. We've got another important wire pair, the DDC channel, which is another wire pair that's a low-speed bidirectional communication channel for EDID and HDCP communication. We've also got our power 5-volt and hot plug wires for the basic handshaking signals. The CEC consumer electronic control wire, a ground wire, and then another wire that was reserved but is now for the Ethernet. And so it's worth noticing that within this structure, the 4 high-speed TMDS lanes that are carrying the most bandwidth and the most critical, these are shielded internally, and then the cable itself, the whole cable, also is shielded. So it's shielded from the external noise, and then also internally is shielded for the crosstalk. So if we look at this, and yeah, we can see that in the world of DVI and HDMI, and generally with transmitting electrical signals, a thicker cable is better. It's got lower resistance. So we typically use the American wire gauge to measure the cable thickness. In this system, a lower number is thicker, and yeah, a thicker cable is better for transmission. Might be a little bit more difficult to work with, but from the point of signal integrity, it's better. And as I mentioned previously, in these cables, there's no separate wire for audio. So with a DVI and HDMI cable and with a HDMI signal, you can send audio through this, and the audio is embedded into the video signal. So there's no separate connection that just handles audio. So even over a DVI connector, which has all of these same connections, you can send an audio signal through that. So now that we've seen how the DVI and HDMI cables look, let's have a look at the Cat-X. So here we've got 3 different types of cable. The simplest is unshielded twisted pair, or UTP. This cable only has the 4 wire pairs and an outer sheath for mechanical protection, but there's a lot of crosstalk between the wire pairs, and it's very sensitive to noise coming from the outside because there's no shielding. So let's say you install a UTP cable and you see it works at a certain resolution. Someone may come along with a mobile phone in their pocket, they get a call, and then you lose the image. That's because the antenna of the mobile is so strong that it's picked up by the cable, so you need shielding. The second type of cable is FTP, so that's a foil twisted pair. This is better because it's got the shielding from the external noise, but it's still not the best because internally there's no shielding, so there's still crosstalk happening inside. And so the best cable in terms of matching up as closely to DVI and HDMI would be the SFTP cable. here we've got the shielding around the cable externally, but then also internally the foil between the different wire pairs. So when we were using older Cat-X transmission technologies, we had a lot of problems with cable quality, and we would always recommend using SFTP cables because, as you can see, they are as close as you can get to the internal structure of the DVI and HDMI cable, in the important sense of having these 4 twisted pairs that are sending the high bandwidth signals. To get them to work as best as possible, they need to be shielded externally but also internally from each other. So that's where we used to have a lot of issues, and as we go forward with HDBase-T, we can see how that technology resolved a lot of the problems that occurred through sending uncompressed video over Cat-X cables using the older technologies. So when you have an unshielded cable with a UTV cable, you send a digital signal through it. It comes out the other side. It's a bit attenuated, but it's still recognizable as the original signal. And as I mentioned, someone comes around with their phone. They get the phone call. The phone starts broadcasting, and yeah, that noise will get picked up by the cable. If we have it shielded, it creates a Faraday cage, and that external noise coming from the mobile doesn't cause any problems. Here we just have a quick slide showing the different variables on the different Cat-X specifications. With HDBase-T, I would recommend at least using Cat6a. You can use it over some of the, you can use it over Cat5 UTP, but you're not going to have a reliable experience. And if you are going to use Cat5, try to get FTP, but Cat6a is where we should all be at the moment. So why do people use Cat-X cables for transmitting DVI and HDMI signals? These cables weren't designed to carry these high-speed video signals, but they have a lot of advantages. They're thin and flexible and easy to sort of string. They're easy to terminate, easy to crimp. They're relatively cost-effective, and a lot of times they're already installed into the structure. On the disadvantages, they can be unreliable, particularly the RJ45 connector. Even if the RJ45 is in there, you can still wiggle it about a little bit and potentially cause a disconnection. Because the cables are so thin, there's a lot higher attenuation. They can be noise sensitive if you don't have any shielding. And this last one is a design feature of the Cat-X cables. There's different twist ratios between the wire pairs, which is great for Ethernet, which is what the cables are designed for, because it decreases the crosstalk, but it also increases the interpair skew. So if we were just taking our TMDS channels and sticking them on these wire pairs, which is what the older Cat-X transmission technologies more or less did, it creates some significant problems. And in light of those problems, we're going to talk about HDBase-T. So luckily, we have a good technology that is designed very well to solve the problem of sending uncompressed digital video over Cat-X cables. HDBase-T is actually based on 10 gigabit Ethernet, and as we go over the topic, you might notice some of the similarities between HDBase-T and 10 gigabit Ethernet. So HDBase-T started off as an alliance between these big manufacturers. They identified the problems associated with sending video over Cat-X cables, and they decided they all wanted to make a solution. Valens ended up designing and manufacturing the chip, and all HDBase-T chips are made by Valens in the same factories. The benefit of this is that there's a high interoperability between the different HDBase-T devices, The downside is that Valens have this monopoly, and so the chips are relatively expensive. So one of the key features of HDBase-T is something called 5-play. 5-play means that over one cadex cable sending an HDBase-T signal, you're effectively getting 5 separate components. HDMI, 10 over 100 megabit Ethernet, an embedded audio channel, RS-232 control signals, and also IR is commonly used here, and up to 100 watts of remote powering. So HDBase-T is a good extension technology. The standard says you can send a signal up to 100 meters, exactly like 10 gigabit Ethernet, but you are actually able to send an uncompressed video signals up to 170 meters over a CAT cable, which is actually a huge achievement. At Lightware, we use our long reach firmware to achieve this. So long reach is a firmware mode that you can enable on all of our HDBase-T products, and effectively it halves the clock speed being used, which means that you can only achieve resolutions up to full HD 1080p, but you can go this extra distance. The amount of heat that the device generates is decreased significantly, and the range of electromagnetic noise that the device is sensitive to shifts. So we've had situations where people with digital radio microphones in a live event backstage, if they were standing within a certain distance, I think it was like a meter, next to the transmitters, they could find that they could knock the signal out. But by switching to the long reach mode, that meant that the frequency these microphones were using stopped interfering with it, and it was a stable system. So it's a nice option to have, to be able to just, if you can, just enable long reach mode, or even if you're getting interference with long reach mode, you can switch back to HDBase-T mode. So you've got an option you can try. So what is HDBase-T and how does it relate to HDMI? Does HDBase-T compete with HDMI, for example? Well, if we have a system like this, it's obvious that we have HDMI and HDBase-T working together. You can see that we're still using HDMI signals because we have HDMI cables. However, in a system like this, where we have a source device that has an HDBase-T output going into a sync device with an HDBase-T input, you might think that HDMI is not being used. To understand more, let's look inside an HDMI device. Here we have an HDMI source device, a Blu-ray player, and a sync device, a flat panel TV. If we look inside the Blu-ray player, we can see there is a decoder reading the disc and taking out the video and audio data, which is then sent to the HDMI transmitter chip. This converts the raw video and audio data into an HDMI signal, which can then be sent over an HDMI cable. On the other end of this, the HDMI signal is sent to an HDMI receiver chip. This converts the signal back into raw video and audio data, which gets sent to the graphics processor and the digital to analog converter respectively. And then ultimately we get our image and sound out of the display. So let's look at the same thing when we're using a HDBase-T device. We still have our Blu-ray decoder sending the raw video and audio to an HDMI transmitter chip. This converts the signal into HDMI, and then this HDMI signal is sent to the HDBase-T transmitter chip, and that gets converted to an HDBase-T signal, which we can then send over our CAT cable and received at the other end, and then we go through the HDBase-T receiver chip to convert back to HDMI, and then we have our HDMI receiver chip, and that sends the video and audio to the same places. So you can see in the system we still have HDMI signals being used, and really we can say that the HDBase-T chip is really doing a format conversion between HDMI and HDBase-T on the transmit side, and then on the receive side it's going HDBase-T to HDMI. So this is the Valens VS100 series chip, which is the original HDBase-T, what we would call full HDBase-T. So that gives you the 100 meters and the 5-play. There's also a Valens VS070 chip, which is HDBase-T Lite. You can tell if a product's using HDBase-T Lite because you don't get the full 5-play, you don't get the embedded Ethernet, for example, and you also only get 70 meters transmission. So to recap, HDMI and HDBase-T aren't competing. In fact, HDBase-T wouldn't even exist without HDMI. So they're very much related to each other. One of the key benefits of HDBase-T is that it emulates perfectly HDMI. So from the point of view of the devices, as far as they're concerned, they're just connected with one long HDMI cable. They don't even notice that HDBase-T is being used. So the signal going through 100 meters of HDBase-T should be the same as if it was going through 5 meters of HDMI. There's no compression or loss of information. So when HDBase-T was released, it was based on the HDMI 1.4 standard, so it supports many of the same features like audio, 3D, 4K, and basically has the same bandwidth limitation in terms of resolution. So UHD at 30 Hertz or at 60 Hertz, but using the 420 color space. So if we look at our basic handshaking, which we've covered previously, just remind ourselves, we have our power 5 volt and our hot plug events that lets the source and sync device know that they're connected up and they're ready to receive. Then we read the EDID. Then if there's HTTP being used, this is where the keys would be exchanged and the HTTP handshake happens. And then we start sending the TMDS lanes, the video and audio. So how does this happen over HDBase-T? Well, there's no dedicated wires for the DDC or TMDS like there is inside an HDMI cable. So the EDID is sent through to the DDC through the HDBase-T device. So we send the EDID as over the DDC to the HDBase-T device. This then gets converted into HDBase-T packets, and it's transmitted over, and it's converted back and sent over to the Blu-ray. Then the audio and video are sent through the TMDS channels. Again, it gets converted to HDBase-T, sent as packets, and then converted back to the display. So all of this happens extremely quickly. So the devices behave just as if they're connected directly through a normal HDMI cable. So it's on the order of less than 1 microsecond. So as we saw with HDMI 1.4, HDBase-T also extends with 100 megabit Ethernet. So in the past, you'd have to connect all of your devices. If you want them on the network, they need their own network connection. But when using HDBase-T, because we're sharing a network channel through the HDBase-T, we can remove a lot of the additional Ethernet and network connections, which is definitely a big help when you're working on an installation. If we take a look at this meeting room example where we have a laptop on the table, we need to get the signal up to the projector on the roof. We can use HDBase-T to send a video signal, but we can also use it to control the projector and send the control signals as well. So we can do it with Ethernet, and we would connect it up like this. So we've got the Ethernet and HDMI connection to the laptop, and then we've got an Ethernet and HDMI connection to the projector, and then in between the transmit and receivers, we just have that one HDBase-T link. We could also do the same thing, but with RS-232. So how is data sent over HDBase-T? Unlike DVI and HDMI, where we have the dedicated wire pairs for specific types of data, HDBase-T is using cadex cables where there are only 4 wire pairs, so there wouldn't be enough wire pairs to dedicate to specific channels. So it's a full duplex transmission over all 4 wire pairs, which means that we have data being sent over all wire pairs in both directions. So we have 2 links, the downstream link and the upstream link. The downstream link is sending video, audio, AV control, which is effectively our DDC channel. So, you know, the hot plug signals and the EDID and all that, Ethernet and IR and the control signals as well. So it's using all 4 differential wire pairs, PAM modulation, which we'll cover soon. It's packet-based, sending 500 million symbols per second, which equates to an 8 gigabits net bandwidth. The upstream link is slower and more limited, but more or less very similar. So we're sending the AV control, Ethernet, RS-232, and IR. It's also using all 4 wire pairs, PAM modulation, packet-based, but the speed is a lot slower. So only 12.5 million symbols per second, equivalent to 150 megabit net bandwidth. So in the beginning, power over HDBase-T was not very well defined. Some of our early devices, we were using a basic 12-volt power setup. This allowed devices to be powered in both directions. However, after some time, POH standard was developed. It's very similar to PoE, is using 48 volts. But it has much like PoE, it has an expensive chip to negotiate sending the power. So with our 12-volt system, you could power the extenders either way. You could have the transmitter powering the receiver, or you could have the receiver powering the transmitter. But it was only using 12 volts, which wasn't enough to power some of the more complicated transmitters and other devices. So this is where the power over HDBase-T came in. So you can transmit more power, but it's not bidirectional. Because you need the negotiating chips, to make it bidirectional, you'd have to have both sets of chips in the same device, and it would actually make it pretty expensive. So it's more designed with a fixed power direction in mind. So it basically works like this. There's a negotiation between the sender and the receiver chip to prevent the power being sent to an incompatible device. Then power is sent over all 4 wire pairs. So much like power over Ethernet, there are 2 categories. There's a powered device, which consumes power, and then power sourcing equipment, which is what sends power. So the key difference between HDBase-T and HDMI or TMDS is that whereas HDMI and TMDS is sending sending the data as a raw stream of bits, HDBase-T is packaged up into discrete packets. Instead of having dedicated wire pairs, we have dedicated packet types. So we've got our video packets, our RS-232 packets, IR, AV control, Ethernet, audio, and then other types of control as well. So it's not dedicated wire pairs, it's dedicated packet types. So any type of packet can be sent down any type of wire pair. If we look at the structure of the packet, it's divided into 3 parts. The header, which tells us what type of packet it is. The payload, where the actual data we want to transmit is stored, and then the CRC for deciding whether or not the packet is sent correctly and whether there's a transmission error. If you're familiar with Ethernet, you might see a similarity, but the key difference is there's no address in the packet. So that's one of the core differences between HDBase-T and Ethernet. So HDBase-T is only point-to-point, but by taking out the address, they could increase the overall bandwidth and payload size. So as I mentioned earlier, there's aspects of cadex cables that mean they aren't particularly suitable for sending the raw HDMI signal. They're much thinner, so they're more vulnerable to attenuation. And as I mentioned in an earlier session, attenuation increases at the higher data rates and frequencies, so it increases exponentially. And HDMI is using much higher frequencies than what cadex cables were designed for. Typical signal paths for cadex cables include patch panels, which aren't a problem for Ethernet, but they can cause reflection and add noise, which is a big problem for HDMI. And the different twist ratios for the different wire pairs, as I mentioned earlier, it's great for Ethernet, but not good for HDMI. So with that in mind, HDBase-T is based on the 10 gigabit Ethernet standard, and there are a few reasons why it's a good technology to use. So Ethernet has been around for over 40 years. It's been constantly improved and is still very widely used. There's clearly doing something right, and there's a lot of resources poured into making sure it keeps improving. Ethernet has a standard 100-meter transmission distance. You can basically do double what you can do with a very thick and chunky HDMI cable through a nice thin cable that you can terminate yourself. Transmitting high-speed digital data over long copper wires presents many technical challenges, and Ethernet has solutions for lots of them built into the standard. And yeah, as I mentioned earlier, the key difference between HDBase-T and Ethernet is that it's point-to-point. In a normal Ethernet packet, there is room for an IP address. In HDBase-T, we don't have that. So by using the 10 gigabit Ethernet standard, HDBase-T gets some nice features. We have error rate measurements thanks to the CRC check that comes with the packet-based architecture. We have reflection compensation, as the Ethernet standard is defined around using patch panels, and so it has an integrated solution for this. The different twist ratios in the CATX cable are no longer a problem. Attenuation can be compensated for, as there is an inbuilt monitoring of cable length and data rate. Different pulse amplitude modulation is used. We will cover this, but it basically means that we can send higher data rates through the cable without increasing the frequency. And by leaving out the addressing information, as I mentioned, we actually have more room in our packets for data, and our packets are simpler and faster to read and process. So what happens when we connect up HDBase-T devices? Well, instead of the basic handshake, we have what's called the startup period, where it actually configures itself for the optimal settings for that system. First, everything is silent and there's no connection detected. When a connection is detected, a training pattern is sent. This is a predefined pattern of information that is used to test the conditions of the transmission. It is used to adjust the different settings until the best possible mode has been selected for this transmission link. And once this process is completed, it starts the normal operation and sends data. So this training pattern and this training part is it's very key for HDBase-T, and we'll see it's also something that happens in DisplayPort. And there's several things happening during this time. So one of the things is that it sets up the EQ level. So the training pattern is predefined, and so what is received can be compared to the known original transmission, and so the EQ can be adjusted until it gets as close as possible to the original pattern. Likewise, you can use edge finding to lock onto the symbols and the borders to eliminate any skew. So by doing this, it can do this on each individual wire pair, so the different twist ratios are no longer an issue because of this. So already we've compensated for some of the most difficult challenges that we had before HDBase-T. Okay, so let's talk about pulse amplitude modulation, or PAM. So as we saw in the earlier session with TMDS, we were using 2 voltage levels to represent binary ones and zeros. So we had a certain voltage level for a high voltage and another voltage level for a low voltage. With PAM, what we end up doing is using more than 2 voltage levels. There are different versions of PAM that correspond to the different number of voltage levels being used. So for example, PAM2 is what we've already talked about, where we've got 2 voltage levels and a high and a low. Each voltage level represents either a 1 or a 0. However, if we want to send data faster in a PAM2 configuration, then what we have to do is increase the clock speed. And if you imagine, if we look at the end of this bit sequence, we've got a lot of transitions. If we increase the clock speed, then the time allowed for the signal to swing between the high voltage and the low voltage gets smaller and smaller and smaller. And to compensate for that, the swing has to get faster and faster and faster. And that's where you start to come up against issues that increase exponentially. So the sort of, to increase the speed by double, let's say, it's going to take 4 times as much energy and generate much more noise. So the power increase for this and the EMI generated increase exponentially. But if we take a look at PAM4, here we've now got 4 different voltage levels, and each voltage level represents a 2-bit value. So by increasing the number of voltage levels, each one represents more information. So effectively, with the same clock speed, we're sending more information. We don't need to swing quite as fast between these different voltage levels because each one itself is actually representing more information. Likewise with PAM8, we've got voltage levels representing 3 bits, and then with PAM16, they are representing 4 bits. So clearly, using higher PAM modulations has the advantage of being able to send more data per clock signal or clock cycle. But there is, as with many things, a trade-off. So the downside is, if we take a look at the distance between these 2 voltage levels on PAM4 and do the same thing with PAM16, you can see that the higher the PAM modulation, the closer the voltage levels are to each other, which basically means it's more sensitive to noise. If we were to introduce this level of noise into the system, with PAM4 we'd be okay because we're still very clearly in that predefined voltage level. But with PAM16, that would easily be enough to skew the voltage level into a neighboring territory and then represent a different 4-bit sequence. So as you increase the PAM modulation, you increase the sensitivity. The way this is handled in HDBase-T is it uses the lower grade PAM modulation for important data. So for PAM2, it's the training symbols, which are used to define all these variables that control the link quality. So you absolutely want to make sure these are transmitted correctly. Then with PAM4, we have the header and the CRC. PAM8, we have the audio and the Ethernet. If you lose audio, you'll definitely notice it. It's one of those things where audio is much more noticeable if it drops out, for example. And it also is not using as much bandwidth, so it can go with the PAM8 without too many problems. With the highest PAM modulation, we're using the active pixels. So if some pixels don't get transmitted correctly and you miss them, because they're being refreshed so many times a second, you'd need to lose a lot of pixels before you actually start to see a problem. So you can kind of think about the different pan modulations in this way. So if we look at an analogy with cars on a road, with TMDS, we have our cars going along, each one carrying one person at a high speed. So you can think of this as our PAM2, where each clock cycle represents 1 bit. With HDBase-T, we can go at a lower speed, which is a lower clock speed, but for every vehicle, we're carrying more people, so more bits effectively. We have some installation recommendations for HDBase-T. The first is to try and always use high quality cables. Whilst HDBase-T does compensate for a lot of problems, it's always best to use cables that are designed for the high data rate being used. If possible, try and go in as straighter path as possible. Coiling up extra lengths of cable can have a bad effect. It's best to avoid sources of electromagnetic noise in the environment. As an example, we have some cases where cables run next to high voltage for air conditioners or different things like that. You can have, when the air conditioner comes on, the cable drops out. 10 gigabit Ethernet standard is rated for use with 2 patch panels. So with HDBase-T, we can follow this, but it's best to avoid anything extra than that, or any patches in general if possible. And when laying cables and building racks and patch panels, it's best to limit the number of cables in a bundle, particularly if you want to reach the max distance. We say that for Cat6a or Cat7, have 6 in a bundle, but if you're using Cat5e, only have 1. And then when you have a bundle, there should be a distance of 10 to 15 centimeters between the bundles. So there's a newer version of HDBase-T being worked on. This slide's a little bit out of date because we're looking at HDBase-T 3.0 at the moment. So 2.0 would be backwards compatible with 5-play, a new feature set called home play, also supporting the audio return channel and USB 2.0. The upstream link bandwidth was increased, so that's from going up to 300 megabits. The downstream links bandwidth is unchanged, and then the idea would be to have multi-streaming support with HDBase-T hubs and daisy-chainable devices, which basically means adding an addressing system. I think where we are with HDBase-T 3.0 is that they're looking at uncompressed HDMI 2.0 point-to-point over CADX cables, which is doing some pretty crazy stuff to get the bandwidths required for that. So to summarize, HDBase-T is designed to complement HDMI, not to replace it. We have the 5-play with the different features. It's using a proprietary coding scheme with PAM16, similar to 10 gigabit Ethernet, but doesn't use IP, and it's less sensitive to CADX cable problems, which was kind of the whole reason it came about in the first place. So there's lots of HDBase-T products out there, and if you compare the features between them, you can normally tell does it transmit something over a CAT cable up to 100 meters? Is it uncompressed? Does it support these resolutions? There's a lot of similar looking products out there. With Lightware, we call our HDBase-T products TPS, and on top of the standard feature set, we try to enhance HDBase-T. So we use a 15 kilovolt ESD protection, which is very high, probably higher than you'd see on any other product. We've got the steel enclosure for EMI protection. The 2 different modes that I mentioned before, HDBase-T and long reach. We give you access to the cable diagnostics information, which is really helpful. and then some of the features that you see on most Lightware products: EDID management, signal conversion between VGA or DisplayPort into HDBase-T, and the audio embedding and de-embedding, and the event manager, which is our sort of limited control feature. So here are some examples of TPS products, but we've got quite a wide range. So before we go on to fiber optics transmission, are there any questions that we can answer?
Yes, so we had one question. I think you covered it briefly, but what is the highest resolution and frequency supported by HDBase-T? So
in the slides, we've kind of been talking about HDBase-T 1.0. HDBase-T 2.0, I believe there are some products out there that can do UHD at 60 Hertz 444, so HDMI 2.0, but they are using a compression technology. I think it's most commonly DSC, digital stream compression. And so that's why the big news with HDBase-T 3.0 is that it's going to be uncompressed. So when HDBase-T 3.0 comes out, you should see uncompressed UHD 60 Hertz 444 over CADX cables. Having said that, the majority of HDBase-T products out there are the 1.0 or 1.x series, which are, as I mentioned earlier, linked to HDMI 1.4 in terms of bandwidth and capabilities.
Thanks. Okay, go on one more. Do you think there will be a switcher matrix for HDBase-T 2.0, and are there HDBase-T to fiber products?
I don't know of any switcher. I think the fact that I'm not a huge expert on the matter, but I know the HDBase-T 3.0 chips that I've heard about are point-to-point. So I think if they were gonna make an HDBase-T switcher, you'd need a technology that isn't just point-to-point. I mean, you can use a matrix switcher, one of our modular frames, to take in HDBase-T and switch it and put it out again, but it's not the same as something like SDVoE, where it's actually sitting on the network standard and has IP addresses and can be sent over a sort of standard off-the-shelf Ethernet network switch. So yeah, I'm not too sure if there are plans to release that kind of HDBase-T switcher.
But we have our MX2 modular frame that's coming out soon.
Yeah, I think that's going to be an interesting one. What CAT-X extension technology we use for that product will be interesting. Sorry, Phil, I forgot the second part of the question.
Let's see where it's gone. I know. I think you answered it. And then the second part is HDBase-T to fiber products.
Oh yeah, sorry. Yeah, I'm not aware of that. So would that be a product that would take in an HDBase-T signal on an RJ45 connector and then convert it into some kind of fiber? I would think that if you're using fiber, you probably just use a sort of fiber transmission technology.
Yeah.
I'm not aware of any products that are combining the sort of RJ45 CAT-X extension technology and the fiber extension technology in one product as a sort of converter. You might get something like a modular matrix where you have some inputs that are HDBase-T and some outputs that are fiber optic. But in terms of transmitting over fiber optics, there are their own sort of chipsets and products that do that.
Yeah, it seems point to point would be either or, and once you have a modular matrix, you can then switch between the two.
Yeah.
Cool. Okay, and that's it for me.
Yeah, no worries. Let's move on to fiber optics. So we'll just be going over the basics more or less. So what does a fiber optic cable look like on the inside? Well, it has a core and a cladding, which are made of either high quality plastic or glass. Then we have a buffer and a jacket for mechanical protection, normally made out of plastic. So what are the advantages of fiber optics? They're not sensitive to electromagnetic noise. There's no crosstalk or skew. There's a lot less attenuation than copper. And for these reasons, you can transmit up to much higher distances. So with Lightware optical fiber products, you can go up to 2.6 kilometers on multi-mode fiber, or even 10 kilometers and plus with our newer products. So what's the difference between single mode and multi-mode? Really, they have exactly the same construction. The only difference here is the diameter of the core. So multi-mode cables have a diameter of normally between 50 and 65 microns, and single mode tend to have cores between 6 and 12 microns. So this difference determines how far they can transmit the signals. Multi-mode cables can carry video on the lower end, let's say 300 meters, although most of our products are doing 700 meters on multi-mode. Some go up to 2.6. And then single mode, you can go up to 10, 20. In some cases, with the right SFP modules, you can even go up to 70 kilometers. So what's the physical phenomenon that allows fiber optic signal transmission? It's called refraction. Every material has a parameter called a refractive index, and it's different for each material. And so when you have two different materials, like water and air in this example, and you transmit light from one to the other, the light direction, or the direction of the light ray, will change at the edge of the two materials. And the angle between the directions is determined by the ratio between the refractive indexes. And what we want to happen is what's happening on the right here. So the light ray here hits the surface of the water at a very steep angle below what is called the critical angle, and so it doesn't go out into the air, it stays in the water. So this is called total internal reflection, and this is what we want to happen inside our optic fiber. So we have some real life examples from refraction. I'm sure you've seen some of these before. If you put a pencil in a glass, it looks like the pencil's bent at the surface, but the pencil's not actually bent, it's the light rays coming from the water. Here we've got this guy swimming in his pool. It looks like his head's in a completely different place, but again, this is because of refraction. So when we shine our laser down the fiber, we have light traveling in all different directions. Some travels out of the fiber at the very beginning and is lost, but others stay within the critical angle and reflected all the way along the fiber and out the other end. So we can see, now that we've covered refraction, we can compare how this works in the different types of optical fiber. So in the beginning, there was multi-mode step index, which had quite a thick core, relatively, at 200 microns. And it's multi-mode, which means there are multiple paths or modes that the light can travel through the cable. The result of this is there's an increased amount of dispersion. So if we shine some lasers down there, you can see that it's possible for the light to take all of these different paths. So this type of fiber wasn't so great because there was a lot of dispersion. So to improve on it, they came up with multi-mode grade index fiber, and this is where we've got a much thinner core, and there's lower dispersion. And the key difference here is instead of there being a big step between the refractive indexes between the two materials, between the core and the cladding, as you can see on the step index, we've got a sort of a straight line edge where all the refraction and reflection happens. In the grade index, it's happening all the way along the path. So the refractive index of the material actually changes on an atom by atom basis, and so reflection isn't happening at one specific point, but it's happening all the way along the path of the light ray. And then comparing that with single mode fiber, where you've got the very, very thin core, what this means is that light can really only enter at one angle. So there's only one path that the light can take, so one mode, i.e. single mode. And because of this, there's much less dispersion, practically none, and the greatest distance can be achieved. So why does modal dispersion limit the distance that we can achieve? Well, if we take our signal, our input signal, and we send it down the fiber, and the light rays take all these different paths, you're effectively introducing skew into this system, much like with the inter and intra-pair skew from our TMDS, where taking a different path means traveling a different distance and ultimately arriving at the endpoint at a different time. The same thing happens with these different light rays, and when they arrive at the end at slightly different times, that's when they superimpose over each other and cause constructive and deconstructive interference, and that's where the dispersion happens. And the result is, whilst at our input side we had this nice square input signal, at the output we have a sort of wavy sine wave effect going on. However, this particular output signal is still, would still be able to be read. It's not degenerated, but if we had even more dispersion, you might get a situation like this where it's now not clear what's meant to be a 1 and what's meant to be a 0. So ultimately, this is why signals can't travel as far through multi-mode fiber as they can through single mode. So some of the numbers about optical fiber. The quality of the cable in multi-mode is determined by the OM number. In single mode, it's OS, and generally the higher the number, the better the quality of the cable and the longer the distance you can transmit. So one of the possible problems you might get with optical fiber transmission can be the inaccuracy of the two fiber cables. So if we take a look at multi-mode and we have some misalignment, well, in the perfect world, everything is perfectly aligned and there's no loss. But because we're talking about the core being in single mode, let's say 10 microns in diameter, all we need is a misalignment of over 10 microns, and now no laser light is getting through. However, with the multi-mode system, the same misalignment means that yes, you're getting reduced power, but you'll still get a signal you can use. And the key here is this is one of the reasons why single mode solutions and products and cables and connectors are more expensive than multi-mode, because the manufacturing tolerances have to be that much greater. Likewise, another issue is dirt. With fiber cables, if you get dirt in them, generally a bad thing. But with multi-mode, there's a greater tolerance for, again, getting that reduced power through, whereas in the single mode system, it can be enough to block all the light. So here we have some just a selection of some different connectors. There's more than this, but one of the most popular ones would be the Neutrik. That's a duocon, which means you've got 2 fibers. It's very reliable. It's got inbuilt dust caps and protection, but it's also backwards compatible with the duplex LC fiber, which is very handy. And then the other commonly used ones are the SC, which is sort of came around in the beginning of widespread fiber use, but is now not as popular. ST is very popular in the military in the US because it's got the bayonet locking, and then the LC connector is now probably the most widespread because of its use in IT and data centers with SFP modules. So we take a brief moment to talk about the electromagnetic spectrum and the different wavelengths. If we look at the output of the sun, we have a large part of the electromagnetic spectrum, from IR with the larger wavelengths down to UV with the smaller wavelengths. Not all of this is visible to the human eye. Only the sort of visible light part of the spectrum can interact with our eyes. But if we look at the spectrum, we can see that we've actually got a continuous spectrum at various different intensities, but it's a continuous continuous spectrum. When we look at the same analysis from an RGB display, as we talked about in the very beginning, we don't have a continuous spectrum. We're only using red, green, and blue, and we pulse those different channels in different intensities, and using the makeup of our eye and the fact that we have cells in our eyes sensitive to these specific colors, that's the way that we can recreate all of the different available colors in our vision, but we're not actually outputting the full spectrum of different visible wavelengths. But yeah, we're using the discrete channels. And with our optical devices, most optical devices use wavelengths in the near infrared, and some of these infrared wavelengths you can still, they're close to visible red, so you can still see some red light coming through it. But typically what will happen is discrete near infrared wavelengths will be used. And here with this OPT device, you can see we've got 4 different channels. In this specific device, these channels effectively act as the 4 TMDS channels. So in this way, we can have the full TMDS signal sent down one fiber. You can multiplex these fibers together, these wavelengths together, using a technology called coarse wavelength division multiplexing. So as an example, here we have 4 different laser diodes, each tuned to a specific wavelength or color. And we take light from these 4 laser diodes, direct them all into the same optical core where they become mixed. All we need to do at the receiving side is separate them from the appropriate photodiodes. So because when you different wavelengths refract different amounts, when you send them through lenses, you can kind of separate them out. So that covers fiber optics. Bill, are there any more questions?
No, there's no questions on the fiber optic part.
Okay, well, let's move on to DisplayPort, and then if we have some time at the end, we can run through more of the questions. So DisplayPort came into being in 2008, more or less. This is what the full-size connector looks like. Note the locking springs that are retracted by pushing the button on the connector. So this is one of the big things that people like about DisplayPort. It has a locking connector as standard. DisplayPort came into being for many reasons. A big one was that there's a royalty fee related to being an HDMI adopter and selling their products. Effectively, each connector, I think, is like 50p or 50 cents or something. which if you're a graphics card manufacturer and you're putting lots of connectors on your products, that starts to build up. So effectively, a lot of the graphics card manufacturers got together with VESA and came up with their own standard, which was a bit more open. So it didn't sort of require the licensing agreement that HDMI does, but ultimately it does a lot of the same things as HDMI in a more advanced way, but the end result is very similar in terms of getting the primary thing being getting uncompressed video data through a cable and onto a display. So as I mentioned, it's the graphics card manufacturers teamed up with VESA to define the standard. It can use 1, 2, or 4 data pairs, which we'll look at in a minute. It's got a similar 8 to 10-bit encoding that is similar to TMDS. With DisplayPort 1.2, it's up to 21.6 gigabits. Much of the same color spaces supported as HDMI. Likewise with deep color, it supports all HDMI resolutions, and we'll look at how some of the backwards compatibility is designed, and similar 8-channel audio as HDMI 2.0. And you could say HDMI 2.0, DisplayPort 1.2 are somewhat equivalent. They're the closest ones to each other. Now it's DisplayPort 1.4, which is out there. You can buy graphics cards that can do DisplayPort 1.4, and HDMI 2.1, which is still kind of on paper at the moment. So the key difference between HDMI and DisplayPort is that DisplayPort is using a packet-based architecture, a little bit like HDBase-T. So rather than have channels dedicated to red, green, blue, and clock, a DisplayPort packet will contain all of those components, which gives it some advantages. So DisplayPort has 4 lanes, but those lanes can be deactivated if they aren't required, which reduces the load on your graphics card. So in terms of providing power through a graphics card output, if you can use a lower number of you can give power to a lower number of circuits, a lower number of lanes, even if you're going at a higher speed, having those lanes powered is going to significantly increase the draw through the card, and ultimately you can draw less power through the card. It'll have a longer lifetime, and generally it's nicer for that side of things. So here we have a brief overview of the DisplayPort connector pinout. There's a lot of similarities with HDMI, but instead of TMDS wire pairs, we have the lanes. We have the auxiliary channel, which is a bit like DDC, but it carries a lot more bandwidth and data. We have the hot plug, but we also have another pin for return power, which can be used in junction with this DisplayPort power pin, which is there to provide power for adapters, amplified cables, and similar devices. So you can send a lot more utility power, let's say, through a DisplayPort connection than you can through an HDMI connection. And then we have these config pins, which are important for detecting whether or not an adapter is in place. So for example, if these 2 pins are shorted out, that can be a signal to the source device that a DisplayPort, a passive DisplayPort converter is in place. So what's the difference between an active and a passive converter? Well, if we take an active converter, that will take a DisplayPort signal in and convert it to HDMI. So the format conversion is actually happening in the adapter. However, if we use a passive adapter, well, as I mentioned previously, the passive adapter shorts out the pins. So this lets the graphics chip know that there is a passive adapter in place, and it will do the DisplayPort to TMDS conversion inside the GPU. So it sends out a TMDS-like signal. However, DisplayPort aren't able to produce the same voltages, which is required for TMDS. So DisplayPort is 3.3 volts, and we need 5 volts. This lower voltage level is also something that gets mentioned sometimes with, especially when you're building larger, more professional devices. You need to keep the internal environment inside that device very clean of noise, because with the lower voltage level, as we saw with PAM, it can mean that it's more sensitive to electromagnetic noise. And so we're sending this 3.3 volt TMDS signal to the passive converter. All that the passive converter does is the level shifting, so it shifts the voltage levels. So single link DVI and HDMI converters are usually quite small. They have very few chips, so they don't require the external power most of the time. However, there's no easy way to visually distinguish whether they're active or passive. Sometimes a manufacturer doesn't even indicate this in their documentation. At Lightware, we always recommend using the active converters because their performance is better, but it's not a guarantee. These adapters are generally have issues with reliability, which is why we started to put on some of our newer products, have this kind of DisplayPort to HDMI and HDMI to DisplayPort conversion actually happen in the product in a way that you can control and is more reliable. We also have DisplayPort to VGA converters. These are always active, but again, they don't require too much power. And then the last commonly used one would be DisplayPort to dual link DVI. These are usually much bigger and more expensive, and they require external power, normally from a USB port. So as I mentioned earlier, there's the similarities between DisplayPort and HDMI. You can really see this when you look at the pin out through a passive adapter. So yes, the main links are similar to your TMDS channels. The auxiliary is your DDC, and it's very much similar to this. So extending a signal is quite a common requirement. So when you're doing this, where should you put the converter, and what extenders should you use? Well, it depends on what type of extenders you have. If you have DisplayPort extenders, then you need to put them where the signal is still DisplayPort, which means you put the converter at the end before the display. However, if you have DVI or HDMI extenders, then you can put the converter at the beginning at the source, and then use the other technology to do the extension. So another key difference between HDMI and DisplayPort is that HDMI is the way the bandwidth's used. So with HDMI, as you increase the resolution, you increase the bandwidth being used. And so the used bandwidth is equal to the bandwidth requirement. With the DisplayPort, it operates in a different way. It has fixed speeds, fixed bandwidths that it uses. There's a low speed and a high speed, and there's also an ultra high speed, let's say. And if the resolution requires a bandwidth that's under the low speed, then it uses the full low speed bandwidth. Once it gets to a higher resolution where there's the high speed is used, then high speed is turned on, and that's the bandwidth being used. So the used bandwidth doesn't equal the bandwidth requirement. There's different outcomes of this. One is that with DisplayPort, if you get a signal at a certain resolution, you're likely to get a signal on many different resolutions as well, because the bandwidth being used is probably greater than what you actually need. So if you need more, then you can probably get it. It also again benefits the graphics card side of things, because the graphics cards can be designed to work at fixed speeds and fixed power draws, and it makes things a lot simpler on that side. However, one of the downsides could be with DVI and HDMI, if you have a system and you've got an unstable signal, it could be that you're coming up against the bandwidth limitation for that particular system, and if you drop the resolution down, you might be able to make something stable and usable. That wouldn't work with DisplayPort. Just because you're lowering the resolution doesn't mean you're lowering the bandwidth. So similar to HDBase-T, DisplayPort is using a kind of link training. We go through some of the same steps as DVI and HDMI. So we have the hot plug event, we read the EDID, then we read the DPCD, the DisplayPort configuration data. So some additional data outside of the normal EDID. And now it will send the training pattern, much like with HDBase-T. So DisplayPort tries to use the least amount of pins. So it starts with the highest data rate on one pin. It tries this, it reads the result, but it gets a failure. So it tries again using more pins, but a lower speed. This time it succeeds, then it can send the video. So this link training is very important. With our matrices and DisplayPort, being able to control the link training was one of the most requested features. So with DisplayPort, there are multiple ways of sending the same signal. You could use anywhere between 1 and 4 lanes. An embedded clock is used, as well as control data. The highest possible bit rate with the lowest number of lanes is the preferred options. Yeah, the control data is always sent 4 times, because if you lose all 4 packets of the control data, then your picture will drop out. So it's quite important. So if we take a few examples for the lane count and bandwidth selection, let's say we have a 720p 60 Hz signal. The bandwidth requirement is 2.23 gigabits. With HDMI, we divide this by 3 between our 3 color channels. And then with our clock channel, we have the pixel clock frequency of 74.3. So all 4 wire pairs are being used. DisplayPort, on the other hand, will see that if it uses 2 lanes at the low speed, that's enough, so it can turn the 2 other lanes off. Or if the link is good enough to use a higher speed, then only 1 lane is enough, and it can turn off the other 3. And in DisplayPort 1.2, we have an even higher speed, which is more than enough to carry this data. But there's no point using the higher speed, so we would stick with the 2.7 gigabits per second. For another example with 1080p, again with DVI and HDMI, we'd divide the bandwidth requirement by 3. DisplayPort, we could do it with 4 pins at the low speed or 2 pins at the medium speed, but with DisplayPort 1.2, we can even do it with just 1 pin at the higher speed. DisplayPort employs something called interlane skewing. With the control data being the most important, it's important not to send all 4 copies of the control packets at the same time. So this is why the interlane skewing is used. So if there's a spike of noise at a certain point, you might lose 1 packet, but at least the other 3 will hopefully come through. So it's used to improve the reliability. So we talk about DisplayPort 1.2, which is fairly widespread. So the DisplayPort of DisplayPort 1. The bandwidth of DisplayPort 1.2 enables it to send 4 full HD signals or 4K 60 Hz. The auxiliary channel is enough to allow high-speed USB 2.0 and a decent Ethernet. And there's a new audio copy protection, which I'm sure there's lots of people having fun with. So one way to visualize it is over 1 DisplayPort connector, you could have all of these other connections. A little bit, again, like HDBase-T with your 5-play, you're getting more different signal types over the same connector. DisplayPort supports multi-streaming, so one DisplayPort cable can carry multiple video signals at the same time. It does this by sending, because you can potentially send your one video signal over one pin, you could then send a different one over another pin. So it's using this feature of DisplayPort. You could build a box like this where you have your 4 signals going into one box, one DisplayPort connection between them, and then 4 signals come out. However, this isn't commonly done. I don't know anyone who's doing this. What's a lot more common is to have a sort of daisy chaining where you can one source creates 4 signals and sends it to the first display, which takes its own signal, and then sends the rest to the next monitor, which takes its own part, and so on. So if we are looking at the future of the DisplayPort versus HDMI question, DisplayPort is going to be sticking around on the graphics cards, that's for sure. There's a lot of features incorporated that means it's the preferred choice for the GPU manufacturers. The consumer market is already saturated with HDMI, and there's a head start with things like HDR becoming available earlier on HDMI. For the professional manufacturers, we basically need to serve both formats. There's a real challenge behind developing professional DisplayPort products. There's many advanced features. As I mentioned, the different voltage level means it's a little bit more sensitive. The fact that there are multiple lanes and many different configurations that you'd have to account for or have all proved very, very challenging. The DisplayPort standard is really only designed around the idea that there's a source device, a cable, and a sync device. So having some kind of device in the middle that does something else is not really accommodated for in the standard, whereas HDMI has made at least some provisions for stuff like AV receivers where you might be switching the signal, and because it is more basic, it's a bit easier to work with on a physical level. So we have recently, last year, released DisplayPort matrix switches, which were something people had been asking us about for many years. Yeah, there was a lot of challenges. If you think about a matrix crosspoint, you're going to have multiple inputs going to multiple outputs. Well, with DisplayPort and the DisplayPort configuration data and the auxiliary channel, there's a lot of bidirectional communication that has to happen. And how will the crosspoint work if there's, it's 1 pin on a high speed or 4 pins on a low speed? There's so many different variables that make it difficult to make professional products with DisplayPort. When you compare it particularly with HDMI, which is based on a DVI standard that's however many years old and is on this much more of a simpler electrical design and closer to the physical level, where you just basically need to connect these wires to those wires and the signal goes through. And so yeah, just as a sort of final comparison between some of the different signal types that we support at Lightware, giving you an idea of the different the features and capabilities. Great, that takes us into the end. So yeah, we've got some time now to go over any questions that there might be. Phil, do you have any?
Yep, we've got some. We've got does DisplayPort support CEC?
I believe that it has its own equivalent. So if we go back to the slide about the passive adapter, there was a pin that gets, when you have the passive adapter in place, becomes the CEC line. So I would imagine that's yeah, if the passive adapter supports it, then it should be part of the standard.
And let's see. DisplayPort, mini DisplayPort, Thunderbolt, are they equal in video bandwidth?
I believe so. So Thunderbolt is kind of built on top of DisplayPort, let's say. So with Apple and using Thunderbolt, you can get very high data transmission rates. You can even do some cool stuff like get an external graphics card and connect it over Thunderbolt, and it goes onto the PCI Express bus. So in terms of transmitting data, you can do a lot of cool stuff with Thunderbolt, but when it comes to the video transmission side of it, it works just like DisplayPort. So it's the same limitations as I think Thunderbolt 3 might be DisplayPort 1.2. I'm not too familiar. I don't personally use Apple devices that often.
And does DisplayPort support HDR, Dolby Vision, and surround sound Dolby, DTS, and RO?
With regards to the audio formats, I'm not quite sure what version supports what. I would imagine DisplayPort 1.2 would probably support those. With regards to HDR, DisplayPort 1.2 doesn't support HDR, but DisplayPort 1.4 does, which is nice. But I think the issue there is going to be, my impression is it's going to take a while for the DisplayPort 1.4 professional devices to really proliferate. We're basically just getting there with DisplayPort 1.2. So yes, if you've got a nice graphics card and you've got one of these ultra-wide gaming monitors, you can use DisplayPort 1.4. But outside of that scenario, I think it's going to take a while before it sort of proliferates into signal extenders and switches and inputs onto different devices. So it's still whilst DisplayPort 1.4, it's great that it supports HDR. In terms of the products out there that are actually being used with HDR, HDMI 2.0 is really much further ahead. Yeah, I know we did a little bit of stuff with the guys at Brompton with their SX40, the Tessera LED wall controller, and yeah, we had a bit of a discussion with them about what input should the device have, and they ended up going with an HDMI 2.0 input for a lot of the same reasons I mentioned earlier about the difficulty in developing DisplayPort products, and then also the fact that you got HDR with it as well is kind of a nice benefit as well.
Okay, and then we have, how come there are few DisplayPort extenders, most of them are HDMI, and why are there no DisplayPort matrices?
So we have a DisplayPort matrix at Lightware. So we have MX2 range. We've got different standalone DisplayPort matrices. But yeah, typically the reason we don't have the extenders or the switches is because it's a much more difficult signal to break down and play with, because it is so advanced, because it's trying to do all these cool things, whereas most of the time we really just want to send video, maybe with some audio. Okay, now we're starting to talk about USB and Ethernet. It gets really challenging. There are some out there, but there's some technical aspects that are just always difficult to do. It's a lot like how it's very easy to convert from DisplayPort to HDMI, because first of all, they incorporated some design elements when they designed the standard to make that possible. But it's typically easier to go from a complicated system or a complicated thing into a simple thing than it is to turn the simple thing into the complicated thing. So going from HDMI to DisplayPort is a lot more difficult. And I think it's only been very recently where you started to see HDMI 2.0 to DisplayPort 1.2 adapters and devices out there. For the, and to get from HDMI 2.1 to DisplayPort 1.4, I'd imagine it would be, again, many, many years before that product gets released.
And what are the practical applications for Lightware DisplayPort matrices in professional AV?
A lot of times, well, from my my experience from the live events environment, it would be media servers. A lot of them have DisplayPort outputs, so you want to, if you've got a system where you need a live and backup switch capability, you could have all of your main and backup media servers connected into a Lightware matrix, and then feeding that out. You could be going into input cards on an E2 or a Spider or an Acrylon that are DisplayPort. Now, with some of these things, you also get HDMI options as well, but it really comes down to what version of what product you have. But that's definitely one. I think basically taking input from media servers or anything which is going to be graphically intensive, the preferred output type is probably going to be the DisplayPort. So if we can eliminate the need for all those passive and active converters and just have the native compatibility, it solves a lot of reliability problems that people have. I know cases where people will do a rehearsal, everything's working fine. The next day there's a problem. One of the first things that gets checked is all of the DisplayPort adapters, and people go around with big buckets kind of like swapping them out because there's there's varying degrees of success with those adapters. Let's say that.
And what's the DisplayPort supported resolution? What's the maximum supported resolution?
Well, with DisplayPort 1.2, it's 4K at 60 hertz, UHD at 60 hertz. I mean, that's the largest standard resolution. Now, with some of these ultra wide gaming monitors, I think they're more or less doing 5K by 2K. Some of them use 2 inputs, so it's really not, you're not actually pushing it, but some are doing it over one input connector. And then you have all of the non-standard resolutions. I mean, it's what I'd say is DisplayPort 1.2 and HDMI 2.0, you can kind of get the same results in terms of bandwidth and resolutions you can support. So, for example, we've done some tests with sort of ultra wide resolutions, so 7560 by 1080. So you've got 7K in there, but the actual total overall bandwidth is still within the HDMI 2.0 and DisplayPort 1.2 bandwidth limit.
And do you see USB 3.0 replacing DisplayPort as a royalty-free video connection on a graphic card?
That's an interesting one. I mean, with USB-C, you have uncompressed video, but that's actually backwards compatible with DisplayPort. So I think that that aspect of USB, particularly with USB-C, you could see that as something that's grown out of DisplayPort. With just pure USB 3 and using something like a nice USB camera, yeah, you can get video through that, but in terms of transmitting that, USB might not be as good as DisplayPort or HDMI for going further distances. It's also how is the what's the pathway for the video data to get on your display? I'd say that with USB 3, you're going through more layers to get to the, to the display. You've got the operating system getting involved, and you're going through, let's say the software layer a bit more, whereas stuff like HDMI particularly, you're very much on the hardware layer, and it's there's a wider level of support there. I'd say you're working on a more basic signal in some ways, which has benefits in terms of compatibility and sensitivity, and for those reasons, I'd say that I wouldn't imagine HDMI and DisplayPort being disappearing because you've just got USB 3 now. I think there's still maybe in 5-10 years, who knows, but I think at the moment, I think all three will be around interacting with each other. Okay, well, I think let's call it a day there. We've enjoyed these webinar sessions. Got some good questions and engagement out of it. We will, as always, be if you've registered for the webinar, you'll get a link afterwards to a recorded version, and we will try and answer any remaining questions as well. So thanks everyone.
Will any of the presentations be released as well, the slides?
I can always send over the PDF version of the slides if anyone's interested. You can, if you want to email me, my email address is felix.knight, felix.knight @lightware.com. And if there's any other questions anyone has, or any further information, feel free to get in touch. Cool. All right, Phil. Well, thanks for joining me again today, and thanks for everyone who made it onto the session. And